Good morning, my name is Chris Tutt. I'm a product manager with Carlisle Interconnect, and today we're going to talk about RF and power and high density interconnects that are associated with that. So some trends we're seeing is the miniaturization and increasing packaging density for interconnects, higher levels of integration, phase match transmission paths, quick interconnect and blind mating connectors, and so forth. So as you can see, some dramatic increases in package increases in density, going from a TMP, which is around the size of an SMA blind mate, to a SMP, then SSMP and WMP, dramatically reducing the size. The mating height of a WMP is about 0.1 inch board-to-board stack height. Solution one, so multi-port push-on connectors. Standard is 2, 4, and 6 port connectors. Custom designs are available. We do anything from 2 to 16 to 32 packages for the blind mates. And they are available in the SMP, SSMP, WMP lines. And they range from DC to 65 gigahertz with low mating forces, and they have straight or right angle configurations available to them. And here you can see the picture on the left is an optical modulator and driver where we have incorporated a 2-port or 4-port PCB connectors onto the module with an edge mount configuration. And then the solution on the right, this is actually used in a military application where we've incorporated 16 SMP bullets, blind mate bullets, on a module that has also a mixed signal D sub, micro D. This is made with a module, goes into a rack, blind mate, the whole module slides into a rack and mates 16 at a time with the micro D connector as well. So what are the challenges? Traditionally, a pin and socket contact, larger connector, not as big of a deal for bending pins and getting stubbing. But as we get smaller and smaller, like a WMP, the contact is so small, and you're trying to gang, if you're ganging 2, 4, 16 connectors, you will not feel it binding and actually bending that pin. So that's the biggest challenge. As things get smaller, you risk bending the pin and stubbing it and damaging the whole interconnect path. So the tolerances are extremely critical to make sure that everything lines up, so it prevents any chance for the pins to break. And then mating forces. If you have a ganged connector with 50, 100 connectors mating together, the forces to mate those is going to be very high. And then the extraction forces is even the more critical part. Is you pull that board off with all those connectors, and you're going to chance ripping off the soldered center contact from the board. So those are some of the challenges. Another solution that we have where there'll be zero extraction forces is a patented product by Carlisle. High density, it's a DC to 40 gigahertz interconnect system. It's a genderless connector, so it uses no male and female pin and sockets. It uses a Z-axis elastomer that connects one connector to the other in DC with a bandwidth of 40 gigahertz. Many different packaging configurations. Here you can see we have it packaged in a D sub. This picture is the mixed signal D sub. So the mixed signal portion does have standard pin and sockets. It's a size 20 contact. It's used for power, digital, I/O signaling, stuff like that if you want to combine everything in one interconnect. Then we also have it in a circular configuration, so a 38999 style connector. It's not actually a 38999, but it uses the same footprint hole pattern if you are mounting it onto a panel. The coupling nut and the keying is different because you don't want to accidentally plug on to the connector. And then we also have board mount configurations or mezzanine connectors where you can stack boards on top of each other with no connector on the board. So you have this pattern etched onto your circuit boards. You sandwich the two boards in between this connector or around this connector, and you have one connector instead of, if you were doing an SMP, you would have two sockets and a bullet to make connections. Here you can see this is a mixed signal configuration attached to the board, and the design is, if this was if you had a backplane, say this is the backplane, you have a module with a board that's coming down with this connector on the end of it, going down the rail and mating directly to the circuit board with no interconnect, no other connector on there. It's another example of where we're using the HDRFI is in an IC test application. So here you can see this is a 20-port connector, and there's no connector on the circuit board. All there is patterns, the coaxial patterns on the board. This mates to it and gets 20 plus gigahertz performance from the connector through the circuit board. And this could be made in different configurations as well. So the mezzanine system. So here you can see the connector I talked about before, but here's another example of a mezzanine connector. This one was a stacked for phased array radar, where they're trying to get thousands of connectors on these circuit boards and keeping on the module that was going to go into the phased array. So there's circuit board on the top and circuit board on the bottom. These two are mating, and then this one was staggered, another level of boards. So this one had 8 circuit boards that were all going to stack together and keep the whole module really dense. But normally, so this connector was going to have 64 connectors across just that one edge. And to do that, the insertion forces was going to be very, very high. Just to snap all those in, you have to get them all lined up. If they were going to have bullets, you'd have to make sure every bullet was perfectly lined up. But this got rid of that. All it had was a couple guide pins and the holes in the PC board to make sure everything lined up. You dropped it in, they screwed the circuit boards to this module, and it made the connection. And then the extraction forces, there was 0. Basically, you unscrewed the circuit board from that block, and it was unconnected. And some different configurations. You can see different shapes. This one has to have 50 connectors, 50 RF connectors in a span of 2.3 inches by 1.25 inches. So it shows you how densely packaged you can get those RF connections. And then some other unique applications. Oh. Any questions? Thank you.